Hello world, welcome to the second day of Cybershock. We are going to shock the world once again, shocking the cyberspace. This event, the technical event, is being created by the CERT.LV, co-sponsored by the European Union, and we've been supported by our partners to run the Capture the Flag event. Our partners, Cybershock Technology, CTF Tech, and TET Group. We welcome you to the second day of the event, filled with different talks, starting with tracking the threat actors, analyzing metadata in the pictures, and understanding how the malware works. With this, I would like to bring on the stage Dan from Kaspersky, who is going to explain and dive into how we're going to capture the attackers. Dan, welcome.
Hello.
Welcome to the cyberspace. The floor is yours.
Can you hear me? Everything okay?
Everything is perfect.
So, I started sharing my screen. Hopefully you will see my slides. Thanks a lot to you for this amazing invitation. It's my first time presenting here. Hopefully it's going to be interesting. We're going to talk about something that we inside my team at Kaspersky we are doing for like in the past 6 years now. And without any further delay, I would like to start. A little bit about myself. My name is Dan, and I'm part of Global Research and Analysis team, which is part of Kaspersky. We are a small team of more than around 40 people all around the world, and we analyze one of the most advanced threats that exist. You might have heard about some of our research, and if not, I will be talking a little bit in the next slides about them. Personally, I've been in this industry for like 6 years since I graduated university, and my main task and what I do within the team is building tools for threat intelligence. So basically handling large big data, building tools, and also helping my threat hunter colleagues, threat hunter researchers, hunt for new malware. I would like to thank Mr. Kostin, my manager, for supplying the slides. And I would like to point out some of the research that we've done. And this is all before 2017, mostly because it cannot fit in, so what happened in 2018, 2019, and now 2020, it cannot fit into one screen. But these are the golden ages of APT research, I would say. And of course, I wanted to mention Stuxnet is not something that we directly researched, but it's something that I think it's the inception, the beginning of those golden ages. And then we start with DoQ, then Flame goes, we start to see more and more families, and as years pass by, we start to identify that there are a lot of APT attacks, APT actors, APT campaigns, unique ones that are being discovered not only by us, also by other cybersecurity companies, and it's huge. But what I would like to briefly, I would like to mention some of them, which are, from my point of view, pretty interesting. And of course, it starts with Stuxnet. This is 2 years since Great was founded. We celebrated in 2018. We celebrated 10 years of activity. So Stuxnet was discovered in 2010, and I think everybody knows about Stuxnet. It was like targeting the uranium enrichment. An uranium enrichment plant in Natanz. It was targeting the Siemens computers that were like handling the centrifuges, and the rest is history. Then 1 year later, we discovered DoQ, which was based on the Tilde platform. It was pretty interesting discovery, and then there was like Flame, Gauss, and Mini Flame. which were again modules and similar with DoQ designed to wipe entire computers. Red October, it's an Eastern European campaign targeting Eastern European institutions, which was built by a Russian-speaking group. They were targeting diplomatic missions, they were targeting embassies with documents about like selling diplomatic cars or like some new trades and things like that. Then Dark Hotel, which is like my favorite one. It's a campaign that was targeting VIP guests in luxury hotels. So attackers managed to infiltrate the hotel network, and because they had access to the guest list, they knew what kind of visitors they should expect in the following months or weeks, and then they would surgically select those important people, the targets they were looking for, and then they knew those targets would targets would connect to the Wi-Fi network. So basically, because they control the network, they were injecting malware into their traffic, into their unencrypted traffic mostly. We had a colleague who tried to spend, he did spend 2 weeks at a very luxury hotel, and unfortunately he wasn't targeted, so he didn't catch any malware, but I think he enjoyed his stay there. Of course, everything was in the name of research, so yeah. Equation 2015, you can see our presentation from Houston with Love. It was from my point of view, one of the most highly advanced APT attacks. It was able to target hard disk firmwares. It was able to have persistence by infecting the hard disk firmware. So even if the sysadmin would perform format, reboot, or like completely wipe the disk, then the malware would reinfect the new Windows installation. So that was like pretty cool. I would also like to mention Satellite Turla, which is a Russian-speaking APT as well. Basically, they used C2s, which had IP addresses for satellite connections. So even if we managed to analyze the malware and we noticed that, oh, this malware connects to this C2 IP address, we couldn't specifically pinpoint to a country, mostly because the area that the satellite is covering is huge. It's like a continent. So we kind of knew which satellite was used. Like they had like some specific registration codes, but we just knew that that specific satellite was targeting like Africa. So good luck finding the C2 server. And of course, the Lazarus group, which were like targeting, they had the huge attack on the Bangladeshi bank, and of course, like their subgroup Blue Norov, stealing a lot of money, financial attacks, and since then, since 2017, there's like a lot of attacks. I apologize for my cat. You know, she likes to play around this time, and then she's confused why I'm not playing with her. Okay, so now the question is, and what we've like presented during our conferences was that we live in a new era, and in this era there's this information war. Some people call it a cyber war, others are calling with other names, but we prefer to call it the information war. And the information war has three main weapons, let's say: the cyber espionage, cyber sabotage, and mass opinion public manipulation. Now, the mass opinion manipulation we will not be discussing today. You can see my research about it. 2 years ago, I had a presentation about disinformation campaigns, and you can see more about this specific component. But today we're going to talk about cyber espionage and sabotage, and from our experience, both of them are using malware. So if you want to defend yourself in this information war, by being able to defend yourself against malware components, you are able to actually be protected kind of like 60%. But let's dive in and let's talk about malware. So today we're going to talk about how can you easily, or how can you add a new tool in your arsenal. And in order to do that, everything begins with friends. So basically, I would like to tell you about Yara, which is a tool, and it's basically a Swiss Army knife of identifying and classifying malware. Yara was built by Victor Manuel Alvarez, and you can find it's open source. You can find it on the Virus.Total GitHub page. And basically, it allows you to create a description, a rule, consisting of a set of strings and Boolean expressions to determine, like, to classify if a sample is good or bad. I'm sorry for my cat. I'm not sure what she wants. I apologize. So how does what does a Yara rule look like? Well, it looks like this. And by the way, if you have any questions, or if you would like to point out anything, or if you'd like to mention something to me, I'm also checking the Zoom chat. So also checking, like, sorry, not the Zoom chat, but I'm checking the chat, and Bernhard is like helping me maybe pass some questions in case you have some questions. So basically, a Yara rule looks like this, and it's pretty simple. Basically, it has like a meta section where you can add some info about this rule. It can be anything, and those meta information, like paragraphs, are not used at all in the scanning of malware files. So in the meta section, you can add the author, you can add a description, anything you want. Then you have the strings section. The strings section is the section where you define what you are looking for. So in our case, we're looking for kind, funny, and imaginary strings. So we define those strings, yeah? And lastly, we have a condition. So any Yara rule needs to have a condition, because at the end, the condition will evaluate to true or false. If the condition evaluates to true, then Yara will print a match. It will say, hey, I matched this binary with your rule. The rule name is here in the beginning. If condition resolves to false, then evaluates to false, then it doesn't print anything. So in our case, we want to have kind and funny strings, but not imaginary strings. So in other words, we want to find real friends. So basically, this is how a rule looks like. And Yara works as follows. You have the Yara engine, and you can have modules on top of it. But with modules, unfortunately, we're not gonna go into depth about them. You can have like the like PE module, you can have like math module, you can have like any module that is written in C and is compatible. You can compile, you can write your own modules. It's like fully extensible. And then you have a file set. You have the initial set of files that you start your hunt from. Of course, there are some Yara rules that can be created without having an initial set of files. But for the simplicity of today's talk, I'm gonna start building Yara rules from files that we already have. And then you create the rule, and then Yara will output detected files and some metadata on detections if you want. So how do you run Yara? Well, it's simple. Yara is a command line tool. I will show later how you can have like a system where you upload your rules on the web, but mainly Yara, it's some command line, so you need to use the terminal a little bit. But don't worry, it's not hard to use Yara, and it's not like super crazy like programming. So you basically run Yara, the options, the rule file and the destination file. If you want to scan a destination directory, then you add an extra argument -r, basically recursive. So how does this look like? Well, let's see. You should be able to see my terminal, and let's move this bar. Here I have the rule I mentioned. Basically, it's written in C, kind of C type language. I have the rule here. So welcome to our webinar. And I will do the following, and then I will explain what I'm doing. So basically, Yara, welcome to -r, and then our malware collection. And you see that it didn't find anything. So in this folder, there's no file matching our Yara. What about in our samples? Let me move this one a little bit to the left. What about in our samples file? Oh, in our samples file, we have a text file or whatever. It's a Linux file. And this file matched. And let's see, it's with ASCII text. So let's go to samples. And we see that we have like two files. So let's see what they are. So basically, I typed the head command, and this file, which is named kind and funny, it has the strings kind and funny. This file, which is kind, funny, and imaginary, has these three strings: kind, funny, and imaginary. So we can see that we can see basically with hex dump as well. So we see kind, new line, funny, and imaginary, and then the other one is just kind and funny. So when we ran Yara using this Yara rule, we matched only. Let's run it again. We matched only kind and funny. So basically, you might ask, Dan, what happens if we want to match kind, funny, or imaginary? Well, we can modify our Yara rule, and we can, instead of this condition, say this or this. Basically, we copy this one and this, bam. And now, when we run it again with the same Yara rule, we see that we matched two files. We matched kind, funny, imaginary, and also kind and funny. You can also use Yara, is this one. So basically, what does it mean? It means that I want to print the matched strings. So basically, I run Yara, print matched strings, the same Yara rule, and on the same folder, and Yara says, I matched this rule with this file, and the matched strings were kind at position 0 and funny at position 5 hexa. And then the same thing for our kind, funny, and imaginary at position 0, position 5, and position B. Okay, so this is it. This is Yara in a nutshell. You can see like Yara has a lot of options here. I won't go more in depth about them, but we will get back to it a little bit later when we will be actually solving an exercise. So I'm going to be a little bit faster here. What can you do with Yara? You can identify, classify, and classify malware. You can find new exploits. You can help speed up incident response. You can classify. You start with a sample, and then you hunt for more samples. You can filter network traffic. And you can build your own private antivirus, mostly because you can have like static rules that you have a collection of rules, and then you can scan your entire system with Yara. If there's a match, it means that you might have an infection. So who uses Yara? Every security company. Like we're using it, like FireEye is using it, like VirusTotal, everybody in the industry is using Yara. VirusTotal makes a lot of usage for Yara, like Linux, antivirus. I think it's also for Windows Claim AV. I'm not sure, I only use it for my Linux servers. A lot of companies in Fortune 500, governments, and spyware developers. So we can see here that they also using Yara in order to in order to hunt to see if their malware has been detected. And how do you know that? Well, from the hacking team hack and all their emails got leaked on WikiLeaks, we can see that they also received some emails from VirusTotal. So this is how a notification, VirusTotal notification rule looks like. So some recommendations. If you want to start writing Yara rules, we recommend you to think Yara as a programming language. So write your code as nice as possible, indent the code, use comments, because you might have to use the same Yara rule 2 years from now. And exactly like what happens in software engineering, where you might not be able to understand what you wrote 2 years ago unless you have some good programming programming practices and like policies. The same can happen with Yara rules. So use comments, indent the code, and use the meta section, because you might publish those results. And when publishing those results, you might want to include some contact info for other people to reach out to you. So a name, an email address, a company name could be useful. So let's see an example of a pretty good Yara rule from my point of view. This was created by manager Costin Raju. I think he's a pretty skilled Yara hunter and Yara rule writer. And basically, we see the name. It's pretty self-explanatory. And then when you have a match, you know for sure that it's an exploit for the Silverlight, written by this guy for a generic exploit. I'm sorry, I have like this crazy allergy from like 2 days ago, and sometimes my nose is blocked. So basically in the meta section, we see that he added his name, he added a description on which files this Yara rule matches, from which hash he started from. That's pretty important because you can go to VirusTotal, grab that hash and analyze it, or you can go to your private virus collection and analyze it. There are some strings and there's a condition here. So I will go a little bit, I will explain the condition a little bit later, but this is like a pretty good Yara. So how does it look like? We recommend using the format like what kind of attack, like APT, the country or the language of the attackers, if you know, or ZZ if else, the actor name and the malware name. So that's pretty self-explanatory. And then in the metadata, we recommend using the following keywords: author, date, version, description, and the hashes where you started from. You can also add last modified, copyright, or Yara versions if you want. For more info, and unfortunately I don't have time to go like more in depth, but for more info, go to like CCCS Yara from the Cyber Center Canada for Canadian Cyber Center for Cybersecurity. Go there and have like a very good information about this one. So you can, if you want to use multiple hashes, we recommend adding the hash version multiple times. But other people, they also use different strategies. So what you can do to detect, like have really good detections? Well, you need to test your rule first. You have to like test your rule and make sure that you use the full word only when the string is short. Unfortunately, the full word, basically, it's a really tricky argument. I would like to, I don't have time to explain it. Please check the Yara documentation and see what it does. But be very careful. You use it only when the string is short. Try not to make rules based only on popular imports and exports. That's very important. Remember to use the file size and always check the header. And I will tell you why. So is this a good rule? Well, unfortunately, no. Mostly because it is using popular imports: get proc address, load library, free library, sleep, winexec, kernel, user, not so good. And it uses a condition of all of them. So basically, that's not quite okay, and I will explain what all of them means. So we scan this rule into our clean collection, and we have a collection of clean files, which is like 30 gigabytes of clean files, and it found no matches. So you might say, oh, hey, this rule, hey, Dan, this rule doesn't generate any false positives. But when we scanned this rule on our bigger collection of like 1 terabyte of files, it generates some false positives. So definitely this is not a good rule. So you might have the opposite problem of catching only one sample. So again, do not use runtime generated strings and do not put all possible criteria as a necessary condition. So in this rule, which is again not so good, the author used like a lot of randomly generated strings, and it asked Yara to match all 19 strings. So 19 of them. They're like from 0 to 18, so they're 19, basically it's matching all of them. So this is not so good as well, because it's not matching a lot of files. Also, it has no additional conditions like file size or header. And it's a code-based strings garbage, so not so good. So what can you do? You can use unique and specific strings. You will use the strings tool, and I will explain how you can do that. You can extract ASCII text strings, but you should look at the results manually. You shouldn't take all the results and add them to a Yara. You should look for mutex names or event names. So these mutexes, which are like used by malware. So yesterday, this is a really good example. A speaker, I think he was from Ukraine, he mentioned that ransomware family, in order to avoid System Watcher, creates sub-processes like process threads to encrypt each specific file with a process. So the parent process only sits there and spawns process threads. And those process threads, they have to have some sort of synchronization. So basically, they need to use a mutex. And that mutex you should use in order to try to match and find other samples from that malware family. No user agents, like very specific ones, Nokia, like nobody these days is using a Nokian user agent anymore. Registry unique values names, typos, software instead of software. So it's missing an R. It's very important because sometimes malware creators, they just forget to use it and then they make typos. PDB paths, like really important ones. Global UIDs, encoded configuration strings, things like that. When possible, use 2 or 3 groups of conditions. The artifacts in one group, a group of specific non-unique strings, and file properties in another section. So let's look at a real-world scenario. Let's say we have a set of samples, and then you are asked to do an incident response because some computers in your network have been infected, and you manage to recover 2 samples. From 2 computers, you manage to recover 2 samples. Those 2 samples are like PE executables for Windows, and you want to start from there. So what do you do? Well, the first thing, so for example, we can see that they are like Windows executables. So they start with MZ, so like 5A4D, and basically you can look through them like hex dump, yada yada yada. Of course, we recommend using Hue program, but I'm using this one, so it's not like a big sample. And we see some strings, you know, proxy, type, proxy, proxy, proxy. Some interesting, then some function imports like user32DLL, winexec. Some functions definitions, or like function imports actually. Okay, so pretty standard, but some suspicious files. What if we do strings on this sample? I'm sorry, strings on this sample. Oh, so pretty interesting. We see that we have like some proxy format. We see that we have like a web page, o.html. Oh, bingo. We have like the command that is being like a cmd.exe. So basically it's like reconnaissance. It's trying to identify the host name. Upload failed. So this might be interesting. Download okay. So maybe it's downloading the second stager. We have James, like pretty okay. C99X. Okay, so those are like pretty crazy, suspicious strings, So I'm doing this statically. So there's no reverse engineering, like dynamic execution. No, I'm doing it statically. I'm not debugging it. I'm just like looking at the strings. Okay, so we looked at 3.6. Let's look at F77. So F77, we see that like some shitty short strings, not interesting, some function libraries, internet clones, okay, ESS get server. So we see other kind of function calls. We see the same proxy, the same format for the strings. We see the same cmd.exe. So, oh, we see c9.exe. Okay, so it's not 99, it's like 9.exe. Okay, so right now we have some info and we have some clues about how we can write our Yara rules. And since I have like 10 more minutes, I will just show you how we wrote this Yara rule. Those samples are real life samples. You can search for them on VirusTotal. You will see that they're like pretty old. I mean, everybody knows about them. But this is how a Yara rule might look to detect those samples. So we start from those hashes. We say like this one and this one. This is in the meta. And then we start with strings. So A1 is proxy, A2 is 0 proxy type. B1 is the actual cmd.exe. B2 is like this one. B3 is this one. I commented them and I will tell you later why I do that. And then like this one is another group, cmd.exe, upload, download, and James. James is like, like everybody can put James in the samples. It's not like a strong indicator. Now the condition. Remember from what I said, that it's really important that you check the file type. So checking the file type can be done very efficiently by looking at the 0 offset in the file, and then you just want to see if this matches MZ. But remember, it's like we're looking at the little endianness, so it's basically 5A4D, so ZM, yeah? And then end, we say any of $$A star. This is a Yara language matching, and basically it says I want to match any variables that have like start with A. So we're matching this any of these variables. Any means can be 1, can be 2, and can be at least 1 basically. And we want to match specifically 2 of these ones, and we want to match specifically 4 of these ones. Yeah. Okay, so basically if we run, so let's say we don't know about these ones, yeah? And if we go and we say Yara, and, oops, sorry. If we go and we say, I will be running Yara, so basically, again, Yara minus R, apt blue traveler, which is the file name, is the name of the file, and then the samples file. If I'm running this one, it's matching those two samples in my samples file. But now I want to hunt for more. So how do I hunt? I'm looking in my malware collection, which is like a little bit bigger. And then we have matches. So those are other files that matched our initial Yara rules, that is Yara rule that is based on those 2 files. And then we want to see how many files we matched, and we see 28. So it's good, but let's say we do some more research and we discover more more strings. So this is our improved Yara rule. We have more strings, same condition, and we will be running Yara again. But this time, Yara will match more files. How many? 36. So basically, because we added more strings, we matched more files. These are like we have in my malware collection. So we go malware collection blue traveler. In my malware collection, actually I have 36 files. So we matched all of them. Okay. I'm looking to see. I have 15 minutes. 20. Okay, good. So basically, this is how we improved. So initially, we started only with 1, 2, 3, 4 strings, and then we added more strings. And from 28 matches, which are here, we managed to find 36 matches. And this is how you work with Yara. You write more stuff, you go back, you run your Yara rule, and then you see you got some more matches. And then you tweak a little bit, you add more stuff, you do some more stuff, you add some more. And then basically you progress. But it's very careful. It's very important. You don't match clean files. So let's talk about elegance and efficiency. This Yara rule is using a module called hash, the hash module. And the question is if it is an elegant or an efficient rule. And unfortunately, I can't see your answers. But I would say that if you said it's not efficient, I would say you're correct, mostly because this Yara rule is trying to match only 3 files with those hashes. So it's good only to match 3 files. So that's it. It's not good to match any other files. It's not hunting for any. Basically, it says, I want to see if those 3 matches exist in your malware library. So, you know. What about this one? This is the Drovorub malware. It's was released in August by the DoD. What do you think? So this is the actual their actual Yara. Well, if you said it's not so elegant, I would say you're correct. Mostly because you have this stuff. So this kind of this is a Linux malware, yeah. So this kind of strings can exist in a lot of packets. This kind of a lot of Linux binaries can use the procnet raw or procnet TCP strings. Secondly, it's using all of them. So if there's a sample that is missing, for example, TR09, this sample will not be matched by this Yara. So unfortunately, it's not so good, not a good Yara. What about this one? What would you say? If you said that it's a good rule, I would say yes. Mostly because it's written by Florian Roth, and Florian Roth is like a guru in writing Yara rules. He's like an expert. You can check his GitHub, Neo23. He has like a lot of Yara rules in there from which you can learn and you can see what you can do. And from the first look at the rule, you can see that it has a description, a license, who wrote it, where you can find him, the date and the hash it started from. It has some strings. It's checking to see if the file header is MZ. He's checking the file size. And he decided that all of these strings should be in the sample in order for this APT17 malware October 17 rule should match. So it's his decision. It's not wrong. That's what he found, but his rule is strong. Like he has like all these conditions. So what can you do to improve your knowledge and to improve your Yara rules? Well, you should test for false positives. It's very important you don't match legitimate files. So how can you build your clean set? Well, you can, and you might laugh, but you can go and grab a Windows XP installation file and install it in a virtual machine, and just copy those files. So I have 10 more minutes left. I will finish on time. You can get like Windows 7 and Windows 8 of installation files, Windows 10 installation files from the Microsoft website. You can grab Linux, OS X installation files. You can dump files from generic Android or iOS phone. Grab samples from Microsoft. There's like this also this link here where we can grab clean samples, and create your repository of clean files. So this is the first step. The second step is creating your malware collection file. So creating the malware collection is a little bit harder. There are websites on the internet where you can download malware files, and then you build your malware collection, and then you start writing Yara rules, and you check those rules against your malware collection, and then you see if you find something more. And then when you have a pretty good Yara rule, you can then hunt, or you can use it on VirusTotal to do retro hunts, or you can use it within your organization. You can deploy Yara rule, and you can, for example, you can do like automate distributed scanning of your entire computers using a set of Yara rules that are provided by Florian, by us from Kaspersky. We provide, with all our blog posts, we provide Yara rules that you can use. Other vendors provide Yara rules as well. So feel free to ping me. I can give you some free online resources where you can get up-to-date Yara rules for latest attacks or trends. And you can use those ones to either protect yourself, defend yourself, or to hunt for more. Lastly, I would like to not promote, just to mention the fact that we have open sourced for like 3 years now our web-based Yara scanner. So it's called Clara. And what we can do with it, you can test your rules for false positives, you can fine-tune detections, and everything is done using a web interface. So instead of using the terminal, which I personally prefer, Clara allows you to use the web interface to actually submit your Yara rules and then scan them on distributed workers in your network. And this is how it looks like. This is kind of like an older screenshot. The web interface looks a little bit different now. But basically, you have a rule or multiple rules, and then you have like an agent, and then on which repositories. For example, we have like a Kaspersky repository, we have a clean repository, and then you see how many files matched that rule matched. So check it out, search for Clara Kaspersky, and then you can find it on GitHub. And with this being said, if you want to learn more, there are two main resources that I can point you to. First of all, go to our X training Kaspersky.com, and you can see that we offer a paid training to learn Yara, like 20 exercises. The first one I showed you today with Blonorov. You can learn more. You can do like a lot of exercises and check it out. But there's also a video from Costin Raiu. At this link, you can see the webinar he did like last month, and where he goes more in depth about the writing Yara rules, the good and bad practices. There's also a special guest who they're discussing, Juan. He discussed about some philosophical topics about writing Yara rules. What are the caveats about doing that? And this webinar is also free. So if you want to learn more, I would suggest go to this like URL, and then you can find at the bottom, you can find the link to the webinar, Yara webinar made by Costin Raiu. Or search on Google, Costin Raiu Yara webinar, and you can find it. Go for the Yara online manual and start writing Yara rules. So that's it. Thanks a lot for your attention.
Dan, thank you for a dive into the Yara world and how can we track threats with this awesome tool. I have a few questions now, and correct me if I don't understand this correctly.
Yeah.
Is the Yara can be applied only on static data that's on the disk, or can it be applied also to dynamic data that's changing, such as stuff in the memory, or something that's been, I don't know, obfuscated all the time?
Okay, so Yara is mainly created to scan static files, and you have like a collection of files and you scan it. But Yara can also be used to scan memory dumps. And I've seen that Apple, they actually introduced in their kernel a way to upload Yara rules and to scan their memory. Now, scanning memory is a little bit tricky because you don't have offsets. And of course, you cannot say at position 0, it's 4A5D. You can't say that because there's no position 0 in the memory. Well, there is, but you can't access it. So mainly Yara is for static, but you can use it to scan also fast changing stuff. So you can scan a memory dump, or like OSX is doing, is scanning some memory processes, process memories, or you can also use Yara to scan PCAP traffic. But I haven't seen it in real time. I think Fortinet is doing it, but I'm not sure. But I've scanned PCAPs after I collected them.
All right, thank you for the answer. Now, you mentioned threat actors. You went through the timeline of the attacks that you've seen, and we've known already in the past in the world. And you also go with the Drovorub malware that's a very recent Linux-based one. Now, are we seeing the capabilities of threat actors that they know that you're going to use Yara, they know the tools that you're going to use, and they try to evade those tools?
Clearly. I'm pretty sure actors are constantly monitoring security conferences. Maybe some of them are here with us right now. Hey, hello guys. But I think they're pretty well aware of Yara rules, and they're trying to make their malware more resistant. And I've seen some strategies of the first stager, then injecting the second stager into memory. So basically Yara, it's kind of hard for Yara to catch, so fileless malware. And apart from that, I've seen a shift with attackers of trying to use false flags. So their strategy is, I will get caught. So I know that after one day, well, I prefer if there was a time where we can catch infections like 10 seconds after they happen. Sometimes it's like doesn't happen. So attackers know that they will be their sample will be identified 1 month, 2 months after, 3 months after. So they're using multiple stages in order to say that, okay, you found my sample. That's it. You cannot go further into your research. And false flags in order to hide their sample to look like something else. But clearly, attackers improved their arsenal, their knowledge, their skills a lot. And I like it. I mean, it's a good challenge.
Of course, whatever brings the challenge to the mind is a challenge worth solving. Now, you mentioned that we can apply Yara also when we're talking about processing data streams. Let's not talk about the static PCAP, but what if we want to do live response? We have a network tap, we're gathering everything that's there, encrypted, unencrypted data. How easy it is to apply Yara rules on this, and what's the speed, or is there a penalty that we have to take into account?
Okay, so in your scenario, and actually this is what we're doing in the company as well, some of the protections that we're doing, would be that you tap the traffic, you tap the communications, and then you store them somewhere. So it's pretty. There are some, for example, Suricata or with Bro, you can actually do live rules over what's there. I'm not sure if Suricata supports a Yara module or like if you do some kind of Yara, but a more feasible scenario would be you tap the flow, you save it somewhere, and then you can apply Yara rules on the PCAP. So that can be done. Secondly, what you can do, you can run Yara on all your computers every day, or depends how powerful or how fast those computers are. And lastly, you mentioned the performance. And yeah, Yara supports only 32 threads. But if you specify 32 threads, which you can use the -p argument, it will use a lot of I/O. So you are capped by your I/O, your disk, basically SSD or spinning disks. And secondly, you are capped by your processor when you're trying to scan a lot of files. So in our collection, with our servers, we managed to achieve a speed of 2 gigabytes per second scanning files. So basically we have like millions of files in our collection. And then Yara would go and open all of them, like F open, F close, F open, F close, bam, 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 bam. And then we managed to, using XFS, using like some optimizations, 2 gigabytes. What those guys at VirusTotal are doing, I think they are doing something different, and they wrote a blog post about the performance. But from what I know, or what I think they might be doing, is that they have all the collection files into one big disk. On the disk, they remove the file system completely, and Yara is accessing the disk directly. So it's about hardware. It's about how powerful or how distributed the hardware is.
Right. Thank you for explaining this. Thank you for the great talk that you gave us today. And I thank you once again for joining us live here in the studio for the Cybershock. And with this, we end the current talk. Thank you, Dan.
Thanks for the invitation. Bye.
And in 10 minutes, we'll see you back again. Stay tuned, because we're going to dive into the social networks and metadata and forensics of those. See you in 10 minutes.